Hi, I'm Piyush. In this video, I'm going to present our paper Test of Time Instilling Video Language Models with a Sense of Time. This is joint work with Makrand and Case. The emergence of foundation models has enabled downstream adaptation on a variety of tasks using a language interface and with only a few or even no data samples. This is particularly useful for videos given the cost of annotation and training on video data. However, despite the massive scale of pre-training datasets, we challenge if video foundation models truly understand videos beyond what can be understood from single images. Specifically, we consider temporal relations in language and ask if video foundation models correctly interpret and ground these in video data. We call this as the test of time. We find that 7 existing models fail this test of time. Then we propose a simple recipe based on contrastive learning to instill this sense of time in a model without pre-training from scratch. We are not the first to raise the question of whether video models truly understand time. Prior work has shown that existing video benchmarks do not sufficiently test for temporal understanding, and one can get quite far with a single image or time invariant pooling of video frames. We create a simple benchmark with synthetic data as our test of time. We consider videos that contain two events, such as a red circle appears and a yellow circle appears. We get a caption for this video by stitching the texts with a temporal relation, in this case before. This is a positive caption. We obtain a corresponding negative caption by swapping the two text segments around the temporal relation. The test for the model is to select which of these sentences is consistent with the time order of video. In order to make sure that our synthetic videos are not out of distribution, we also perform a control test where there is only a single event in the video, such as a red circle appears. We pick 7 existing video language models and run this test for them. On the control task, all of them perform very well, as one would expect. However, on the test of time, all of them perform nearly randomly. So, can we do something about this? It turns out, yes, we can. We start with a pre-trained video language model and run another round of pre-training, often termed as post-pre-training. For this, we make use of a dense video captioning dataset. From a single video, we take any two non-overlapping clips and stitch them in time and stitch the caption accordingly with a before or after relation. Note that for this example, we can construct a negative in two ways. Here, we get a positive pair when the video and caption have a consistent time order. Likewise, we get two kinds of negatives, one where the text is swapped and the other where the order in video is swapped. We start with video clip, a pre-trained video language model. The video is cut into 1 second segments. STD features are computed and these are passed through a transformer encoder initialized from BERT. We then get the final video representation by mean pooling transformer hidden states. Likewise, text is tokenized and passed through a BERT encoder to produce the sentence representation. We start with the usual contrastive learning setup where for a video, the corresponding sentence serves as a positive and all other sentences in the batch serve as negatives. Then we apply the time order reversal function to the sentence, which swaps the order of events in the text. These serve as additional negative sentences. One for reverse sentence corresponding to the video, two reverse sentences for other sentences in the batch. Likewise, we apply the same function to the video to construct its time order reversed version. Finally, note that the time order reversed video and time order reversed sentence can additionally serve as positive pairs. We apply standard contrastive laws and use different hyperparameters to control the impact of each of these parts of the similarity matrix. We term this recipe as TACT, temporal adaptation by consistent time ordering. As a baseline, we consider only applying the usual contrastive laws on the top left quarter of the matrix. We call this as the non-temporal baseline. We experiment with TACT on 4 diverse datasets: Tempo, ActivityNet, Charades, and Charades Ego. We create artificially stitched clips as described earlier. We consider two tasks. One, text to video retrieval, and second, our test of time. For retrieval, we look at usual metrics such as recall at 1. For test of time, we look at temporal accuracy, which is the fraction of test samples where the model correctly associates a video with its time order consistent sentence. In comparison to the baseline, on all datasets, we observe that the retrieval performance is either maintained or improved, but more importantly, the temporal accuracy significantly improves with our TACT adaptation. We also evaluate TACT models on the original synthetic data. As expected, TACT performs much better than random. Since we train TACT with before-after relations, it is natural to ask if it truly understands time order of events in videos, or is it only latching onto these words. To probe this, we additionally run an evaluation of TACT models on sentences such as first event 1, then event 2. On this new unseen prompt 2, TACT does much better than chance. This indicates that TACT is indeed learning time order of events across video and language. Furthermore, we ask if models adapted with our narrow definition of sense of time can benefit more general temporal reasoning tasks. To answer this, we take TACT models and evaluate them on the following task in a zero-shot manner. First, we consider temporal benchmarks such as something something and temporal subset of kinetics. On these, we run the action to video retrieval task where given text description of an action, we want to retrieve the most relevant videos. Second, we consider temporal question answering task where the questions have a temporal aspect such as before, after, during, while, etc. We find that TACT adapted models show promising benefits over non-temporal baseline on all these tasks. In summary, we propose a test of time benchmark demonstrated on synthetic and real datasets to check time awareness of video language models. We show that existing models fail this simple test. As a solution, we offer a simple recipe to instill this sense of time. Finally, we show that this recipe has promise beyond the temporal relations we consider and to more general temporal reasoning tasks. Thank you for your attention. You can check out the project page and code through these QR codes.